So yeah, welcome everybody. I'm very pleased that after this multi-copter heavy morning, I conclude the morning with a bit of fixed-wing fun. Yeah, briefly about me or my story with planes. That started a very long time ago. I was always building small paper planes and wooden planes, threw them around the house. And yeah, some Christmas I got this first electric glider here from my parents. From there on, the planes got bigger, more elaborated. Another key moment in my life was then the graduation thesis for my high school, where I built this solar-powered airplane. And that set me up for, also pursuing a degree in robotics and control, which was then done with ETH. And you see this tail sitter here. That was the platform I used for my graduation thesis there. Also got into contact with VTOL and PX4, something that then massively intensified over the next years after I joined Lateral, where I did lots of integration trips in the beginning. So this is actually the first plane I flew in the first couple of weeks after joining 7 years ago. From there on, I was co-maintaining the fixed-wing and VTOL stack ever since. Now, briefly for you guys, when I feel the pulse of you. So who in the audience has ever flown a fixed-wing drone before? Nice, that's super cool to see. Who's ever developed on a fixed-wing drone? Nice. Who has ever developed using ROS and PX4 together? Wow. Who has used ROS with fixed-wing? Okay, let's try to increase this. So what are we talking about? We're talking about APIs, so interface between different software components. In our case, actually, there's even a hardware boundary in between. So we have on one side the FMU that's running our beloved PX4, different control modules, drivers, estimation modules, all real-time, all very stable, but very limited in flash and memory and everything. It's really limited, right? And then that's why we have the option to extend abilities with the companion computer, usually running ROS2, having ROS nodes inside. Way more powerful computer, much more ability, a huge library online, and a very simple interface in between. Thanks to the DDS bridge that bridges between the two components, and us using the PX4 messages inside ROS natively as well. So we have a deep integration of PX4 inside ROS. What that means is that the same messages that we use internally in PX4 to communicate between modules, we also use to bridge over to ROS. That makes it very straightforward to use both roles, and also it means that to understand the interface, we have to talk about PX4 internals, and that's what I will be focusing now in this talk. Hasn't that been covered before? Yes, it has, multiple times. Most recently, or in most depth, in the last Dev Summit by Beat Küng and Thomas Tasny, where they presented the novel way of doing this kind of off-board control, using this, the new PX4 ROS library, interface library. All that was presented back then is still very much valid, so I recommend everybody to watch this presentation again on YouTube if you haven't done so yet. What didn't exist back then, though, was a high-level fixed-wing interface. It was very much focused on multi-copter and some low-level interface for fixed-wings, but nothing high-level. That's something we had to first actually enable inside PX4, rework lots of our control modules to actually cleanly offer this interface to PX4 controllers. We have done this last year, and that was the motivation for my talk today. So what's the fuss with fixed-wing? Why go through all this pain? Well, first of all, distinction between rotary wing and fixed wing is very simple. Rotary wing have a rotary wing that keeps them airborne. It allows them to fly like stable on site. They don't have to move actually. But due to various physical reasons, they are much less efficient, have reduced flight time, less speed than fixed wing have. So fixed wing, they move the whole body through the air, and through that generate the lift to keep airborne. what that means is, yeah, multicopters can fly any arbitrary envelope. They can stop in air, rotate, fly somewhere else, or fly any kind of steep flight path angle upwards and downwards. While fixed wings are really limited there. They always have to keep moving forward, or otherwise they fall down. And that has to be taken into consideration for the controllers and massively limits the possible flight paths. I will now do a deep dive into the system diagram, which is crucial when we talk about APIs. I'm going to fill up this controller section here one by one, actually go through the PX4 manual modes, not because this talk is mostly about autonomous flying, but I think understanding it, the manual modes are actually offering a very intuitive and more tangible grasp to it. So I'll go through PX4 manual modes one by one and explain which PX4 controllers they're touching. Starting with the full manual mode, there the pilot gives normalized torque set points into the system, and all PX4 does in the control side is mixing those inputs to deflections on the servos. Thrust is also directly fed through from the remote control to the actuators. Next up, we have acro mode. In that case, body rate and thrust is set by the operator. This is the first mode that requires some kind of feedback from the sensors. In that case, it's the rates that are passed through the estimator and fed back into the rate controller. That mode allows you to fly very dynamically. For trained pilots, it's an amazing mode, but of course requires a lot of practice. That's why for beginners, usually stabilized mode is what they start with. Here, like without any inputs, the vehicle just keeps its attitude stable, and the pilot can give roll and pitch inputs as well as direct thrust. Need to note that for fixed wings, you cannot set the yaw angle directly because it's always coupled to your motion. You cannot fly backwards through the air, so you have to gently nudge the vehicle in one side. You give a yaw rate input, and then at some point you end up at your desired heading. So while Stabilize is already quite beginner friendly, it still has direct throttle control, so there's nothing helping you to prevent underspeeding or overspeeding of your airplane. This mode here, altitude mode, is the first mode that does that. So here the inputs are roll, height rate, and airspeed. Those are fed through the mode manager module that's grayed out here because it doesn't do anything in this mode. It's just like pass through. And then we have this lateral longitudinal control module that I will talk much more in depth later. But this is basically then transforming or doing feedback control on the set points with the estimator feedback of airspeed and altitude to output attitude and thrust. The next up mode would be position mode. We now adhere to the new MAVLink standard modes definition and call it cruise mode, but it's the same thing. Here, the only difference to the altitude mode before was that you have if you don't touch your stick, you have a course hold, so the vehicle will fight automatically against the wind and not be blown away by crosswind. And to do that, the mode manager now, this module comes into play, where it does a feedback control on the position fed back by the estimator. That concludes the manual modes. That's the full list of PX4 supported manual modes. From top to bottom, they get more augmented, more autonomous, more simple to fly, but also requiring more sensors. All right, then very briefly for autonomous modes. All that's added now compared to the previous position mode is that we have a navigator block in front of the mode manager. That block does the translation from a mission file provided by the operator through mission file or through single MAVLink waypoints into workable position set point triplets. But otherwise, it's exactly the same control structure as before in the position flight mode. So how do we use all the information that I now gave to you for external flight modes, external commands? Actually, it's very simple. So all the same interfaces that are settable or controllable by an operator manually can also be exposed to the ROS side. So all these like torque set point, rate, attitude, and the new lateral longitudinal control set points are exposed to ROS. And yeah, it's important to realize that I always added more and more blocks to the left side, and everything that's right to the new blocks still has to be configured and tuned properly to function. So if you feed in a torque set point, or you only care about the control location. If you feed in a lateral longitudinal set point, then you care about lateral longitudinal control, attitude control, rate control, and allocation. So you have to configure much more things. So the ones more familiar with PX4 probably are confused. What is this new or weird name, lateral longitudinal control? Where is our fixed wing position controller gone? So we had to split this up into these two new modules to enable actually this clean interface to ROS. So previously there was one big chunk of code that did everything from like set points generation to actually feedback control, and now it's cleanly set up into a mode manager that does the set point generation and then a handler on the controller side. I will now deep dive into that part. So actually it's two separate controllers that are in the same modules, the same interface, but they have two completely separated control flows. Starting with lateral control. So that's the controller that in the end makes the plane move to one side, like, or keep a course, or fly a circle, and so on. Starting with a bit of definitions and explanations. So the speeds we care about are airspeed, that's in direction of the vehicle heading, and the ground speed. And if in case of wind, those two speeds are different, and you can actually calculate the ground speed by adding the airspeed plus the wind speed. These speeds are defined compared to true north with a heading and course angle, and we always assume now, it's a bit simplified, we assume now no side slip, which makes assumption very simple that we always have the heading aligned with the airspeed vector. So how do we make a turn with a fixed wing? To bend your turn into one direction, or you bend your course in one direction, you have to create some kind of lateral force, which for a fixed wing is simply done by tilting the whole plane in onto one side. That also tilts the lift vector and creates a sideways force. So with that in mind, we can actually now define the interface, which is consisting of course, airspeed, direction, and lateral acceleration. The interface is structured in a way that you can set any of these three states, and that's then being fed into the controller. So you can set a course or a direction of the airspeed, or vehicle heading, or acceleration. And the thing with acceleration is also that you can always add this also with the other two set points to add a feed forward, such that you can actually do a nice circle, a consistent circle. That's it for lateral control. Now longitudinal one. So that's the controller taking care of your altitude and your airspeed. Talking about that, it's crucial to understand a bit about energy conservation. So a plane flying at a certain altitude, a certain speed, has a certain energy that's in the kinetic and potential energy. And by just pitching up your plane to curve the flight path, you increase the potential energy, and with that you always reduce the kinetic energy. What that means is that you would stall at some point if you just pull on your elevator. That's where our total energy control system comes into play, that handles the airspeed versus or with altitude controller, and make sure that we have a balance of both these requested states. The set point for longitudinal control consists of 5 fields, we can either set altitude or height rate. We can set an equivalent airspeed. I'll leave it up to you to look it up. It's in the end, for most application, you can just consider it being airspeed. Yeah, that can be set independently of the altitude ones. And then we have the way to bypass the whole text controller and set pitch and throttle directly. In some conditions that's desirable. For example, for takeoff or special maneuvers, you want to actually override whatever text would be doing and just set a direct throttle, a direct pitch channel. Yeah, so that's the set points for lateral longitudinal control, but of course there's always more to it. I've talked about the set points, but there's also configuration messages being pushed or fed into the controller. That's crucial to configure the controller for special flight states. For example, for takeoff again, or for landing, or for any kind of gliding, so special out of the normal operations. So the important part with this configuration set points is that they stick. You send them and they stick to the controller until you set a new value, or you switch the flight mode. And on the lateral side, we have only one field here, the maximum lateral acceleration. That's basically to limit your roll angle when close to the ground. And on the other side, we have a pitch that can be limited, throttle as well. Then the climb rate and sink rate target, those are basically the slopes of my altitude controller. So you can make it slower or faster to reach my new set point. Yeah, and then we have three very much tech-specific fields that can be set. The speed weight is to balance between prioritization of airspeed versus altitude. So, for example, a gliding plane wants to have full priority on the airspeed, do not stall, while it can't really control altitude directly. And then we have the two flags for slow height condition and disable ground underspeed protection. Those are really set in special flight states. For example, for landing, you don't want to have your low airspeed check hitting when you're about to flare your vehicle. Okay, so now we're leaving actually PX4 behind, and from now on we'll be completely on the ROS side. More specifically, using the ROS to PX4 interface library that I mentioned before. I will not do a deeper dive there. There's again this amazing talk from 2 years ago of Beat and Thomas on YouTube. They did a step-by-step guide, how to set it up, how to use it, and I just now focus on implementing some very specific fixed-wing features in this new library, or with the new library. Yeah, so we have documentation online for how to use set points in the library. In that case, it's a fixed-wing lateral longitudinal set point type. I will not go in more detail here, but I will show you a simple example. So there's plenty of examples in the library. You can just start with any of them and then add your own fields. In this case, I only had to add 3 lines to it to make this work. So I had to include the new message type that I'm using, so the fixed-wing lateral longitudinal message. Then I had to create a set point that's then being published by ROS, and I had to populate this set point. In that case, it was with an altitude 450 meters above sea level, and the course 90 degrees. Actually, it was 100 meters above sea level. Anyway, that looks then like that in this example. I can switch into my external mode, and it just jumps to the set point I gave. So it will climb to 100 meters above ground, and it will keep the course due east. So that's all done by just these 3 lines. Now then, and a bit more elaborate example would be to enable gliding. So in this example, I wanted to constantly go up and down, like climb to 100 meters and then go down again by switching off the motor and just using gliding. I've set the altitude set point first to 120 meters with a constant lateral acceleration of 3 meters per second square. That will just make it basically turn at a constant roll angle. And then I'm using now the configuration message I mentioned before. Here I have to distinguish between if I want it to have it gliding, then I set the speedway to 2, which is full priority on airspeed. Otherwise, 1 is the medium between prioritization of airspeed and altitude. And max throttle, that's the way to disable the motor for the gliding phases. Yeah, how does that then look like? So here again, I switch into the mode. It now starts to glide. You can see the throttle percentage drop to 0, while it still maintains a close to trim airspeed. It goes down to 20 meters, switches on the motor again, climbs up, and continues doing that forever. This is pseudocode. There's a bit more logic involved to make the switching between the motor on-off, but it's very simple, just based on telemetry, altitude telemetry. Yeah. As you see, it's not really stable at one place. It's drifting over the map. That's because I'm using this lateral acceleration directly field. So it doesn't have a feedback controller running and controlling it actually at one place on the map. So that's one thing that we want to add in the future. We want to actually provide full path segments from offboard to PX4 that then we can track inside PX4 with feedback. That can be any kind of segment, Stubbins paths, lines, circles. Yeah, that's one thing. Other thing is we're still heavily relying on Euler angles in all over the place in the PX4 fixed pin control modules, and we want to reduce our dependency there. Also to enable, of course, flying upside down or just exceeding our 90 degrees pitch limitation that we currently have. That will be requiring a lot of controller rework, and we probably need to start in the more attitude controller side of things. That concludes my presentation. Happy to answer questions.
Hello. All right. Hello. All right. Are there any questions? I know you want to go lunch, but I'm sure there's questions. I'm going to start here. There first? Okay. Where? All right. I'll come back to you. So you're going to have to fight for the microphone. Who wants it first?
Oh, you're doing it for me. Yeah, just a quick clarification. You mentioned and the controller doesn't account for side slip or doesn't assume any side slip. Is that just part of the controller, or the rest of the full loop accounts for a side slip?
No, we don't.
No. So if you were to, so how do you manage that if you're flying an aircraft and you're?
So we have a third coordinator in place that always aligns the vehicle heading to the right place, right? Okay. And for very dynamic maneuvers, of course, you will have some side slip, but usually it doesn't matter that much on the big scheme of things.
Okay. And do you see any reason this couldn't be applied to boats?
Which exactly? Which part exactly?
A boat, any boat, a surface vehicle.
The whole infrastructure.
Yeah.
Well, they have pretty different dynamics, I would say. I mean, guidance already be using similar controllers for boats, but then, of course, there's not a roll angle you give for boats. It's an acceleration, and we also don't measure water currents, while we do measure airspeed, wind speed. So that's a couple of differences that need to be very carefully checked.
Hi, my question is actually related to that. Since we don't account for side slip, we've had some issues previously with like mapping payloads and stuff. Like just because we're flying sideways the whole time. Is there any work that, that's on the map for considering for side slip?
Well, usually it was side slip. It was not just a crab angle. I mean, one thing is that you, of course, fly sideways compared to ground if you have a high wind speed from the side. But usually side slip should actually vanish in your stable forward flight.
Understood.
So probably that was more the crab angle you have from fighting against the wind, and that's something that's just it's physics in the end. You have to align your airspeed vector to be pointing against the wind.
Makes sense. Thanks.
All right, nice. Are there more questions on this side? Oh, it's a bit tight here, so I'm gonna hopefully do not break anything. This is you. Oh, sorry. There you go.
So it's a nice low-level integration where you got the different controls. Does Offboard offer that too, or is that like a ROS exclusive?
You mean offboard, the legacy PX4 offboard mode?
Correct.
That offers actually even more. You can interfere almost anywhere in PX4 with offboard, but it's not a really clean interface. Like, you also can mess up internal things of PX4 very, very easily, and you have not a tight control over it. And also, there's only one offboard controller. You cannot switch between different external modes. While with the new interface, you have an option to go into a gliding mode, go into a soaring mode. I don't know, but different external modes, and they also always fail back to an internal PX4 mode in case they get unstable.
Just a little bit of follow-up. I'm just curious, what's the motivation of making the new ROS2 library versus the old legacy PX4 offboard? You can elaborate. Thank you.
You should actually watch the YouTube video I referenced in the beginning. They actually talk about this in depth. For me, it's just having control, clean APIs, and multiple external flight modes assignable. And just it gives you way more flexibility in a cleaner way. But please watch the other video.
Yeah, just to add to that, like he was saying, offboard is a more complex API and it's prone to errors. And the new ROS2 interface is much cleaner and it's more developer friendly. So we encourage you to switch over. But if you already have something running on offboard, feel free to continue using that. All right. Any other questions? All right. Well, thank you, Silvan.